Hi, welcome to another Unity 3D tutorial. In this tutorial, we're going to have a quick look at the new Unity job system, and we're going to do it by examining how we can make a terrain made out of cubes, as you can see here, run a little more efficiently. What I've got here is a whole bunch of cubes that are following a Perlin Noise wave, not unlike the cubes in Minecraft do. And if you've had a look at one of my Minecraft courses, you'll know that using plain old cubes is not the way to go, and that there's a few tricks to get it way more optimized. But for this tutorial, and just to have a look at how the job system is going to make things just a little bit faster, we're going to use the simplicity of cubes. Now, we'll also have some background knowledge that I'll assume from Perlin Noise. And if you follow this link here, it'll take you to another YouTube clip of mine which explains what Perlin Noise is. But in a nutshell, Perlin Noise is a mathematical equation that goes on forever and ever and ever and gives you sloping up and down height values that you can then use on a landscape rather than random, which doesn't look that realistic. All right, so let's get started. First of all, you'll need Unity 2018 and open up a new project. In your new project, you'll need a scene which has a main camera, a light, and an empty game object called landscape. I've created it here. I've already added some script to it, which you will do in a moment. Now, it's positioned, and that's not really important, as long as when you press play that you're going to be able to see it. So I've just got it at the default 0, 0, 0. Onto that landscape, we're going to add code that does everything for us, including building the cube. So down in the project window, you want to right click, go to create C# script, create yourself a script called Perlin Scroller. Grab that script and attach it by dragging and dropping it over onto your landscape object. Now let's have a look what's in this script. There's a bit to go through. This first lot of script has nothing to do with the job system. Okay, it's just setting up a scenario that's going to create a scrolling landscape of cubes using Perlin Noise. Later, we're going to optimize it using the job system. So let's go through this code. Now, I've done a lot of stuff with Perlin Noise and cubes and landscapes, and you can find a lot of those other videos in this YouTube channel. So I won't spend a lot of time on the theory, though there is something new I'm doing here that I haven't done before, so I will spend maybe a little bit of extra time just showing you what is happening. Okay, so let's go. First of all, we have an integer at the top for cube count. This is going to keep a hold of all of the cubes. So we're going to generate all the cubes that we need to sit across our whole landscape. We're then going to create a matrix, a 3D matrix, so a cube of our cubes. And it's going to be 500 in width, 500 in height, and 3 layers deep. Now, this terminology might seem a little bit unfamiliar to you if you haven't done a lot of landscaping stuff before, because usually when we talk about like a height map or something, we talk about the width and the height, whereas the height really, if you look at it in 3D, the values for this kind of depth here is going back into the screen. It's not the height of the actual terrain itself. That's how many layers there's going to be here. And you can see from my illustration on the screen what I mean by this 3D matrix that we're going to use. Now, moving along, we've got an array of cubes. It's just a one-dimensional array of cubes. We'll be dealing with it as one dimension, but we're actually going to be storing a 3D matrix inside there. Then we have our awake method, and what it's doing is creating our cube count to give us the number of cubes that we need, and that will be the width multiplied by the height multiplied by the number of layers, because that's the total number that there will be in that 3D matrix. We're creating a cube for every single position in that matrix. Then those cubes will be created and populated in this cubes array using new cube object cube count. So this will make it big enough to store them all, and then down in start is where we will actually create each single cube and loop through that entire 3D matrix and dump those cubes in there. So there's a create cubes method that's being written just below here. Let's bring that up, which will create all of these cubes for us. So it's a public returns a game object array. It's called create cubes and includes the count of how many we want. Inside there, we then create a temporary array to hold our new cubes. We then create a cube to copy, which will be basically it's a prefab. We're creating a prefab on the fly here and putting it into our 3D matrix. For the cube, we're using create game object.create primitive type .cube. Now, instead of all of this code, you could create yourself a cube and pass it through as a public variable via the inspector into this script, or you can do it simply like this. We're also going to get rid of a few things as far as the renderer on it. We're grabbing the mesh renderer and removing its shadows or turning those off just to, I guess, amp up the optimization in this case. And we'll make it so it doesn't receive shadows either. You could leave those on with these kind of smaller terrains. It doesn't really impact that much. The other thing we're also doing is get rid of the collider. So we get hold of the collider on that prefab and we'll just turn it off with enabled.false here. Then we will loop around for the number of cubes that we want. So for count, loop around and put one cube in each position in that 3D array. Now inside here is where this loop gets a little bit tricky if you haven't worked with flattened arrays before. So before we come back to looking at this, let's just have a look at how you might be familiar with this type of system. A one-dimensional array, which is represented as a line of boxes in memory, is in a straight line. Each box has an index value, and we refer to that index value usually as an I counter when we create a for loop. And the for loop to loop through this entire one-dimensional array would be a single for statement like this. So if int I equals 0, for I is less than the length of your array, then add 1 to I to go from one box to the other. For a two-dimensional array, we now have two directions. We have a height and we also have a width. And we usually have a nested for loop, which has two index values, j, which tells you which row you're in, and I, which tells you what column you're in. And they can, of course, be called something completely different. We'll go with I and j for now. For a three-dimensional array, we now add a number of layers. So we not only have rows and columns, but we have multiple sets of rows and columns and one lot in each layer. So for that, we need an extra nested for loop. In this case, I've added one called K, which will loop through each of the layers. No matter how you think about it, computer memory is essentially one great big long line, and it doesn't matter how you want to visually structure it or structure it with your for loops, that doesn't change how it is physically structured inside of the computer, and you're always dealing with one great big long line. So no matter if it's a one-dimensional, two-dimensional, or a three-dimensional array that you've declared, or 4, 5, 6 dimensions, it can always come back and be represented as a one-dimensional array, and you can access all of them with just one for loop. The only issue doing it this way is that you've now lost access to the individual rows, columns, and layers, and you have to convert the value of I, your index, back into a system that makes sense in 2 or 3 dimensions. When you flatten a two-dimensional array, so instead of declaring it as an int that has a width and a height and 2 dimensions, reduce it to a one-dimensional array of size width times height. From the single dimension, you can work out what the x and y values are, or which row and column that you're in, using I divided by width for the x and I mod height for the y. When you flatten a three-dimensional array, it goes from having 3 indices, width, height, and layers, to a single value where the array length is width times height times layers. Then to access each individual position so that you can tell which row, column, and layer that you're in as far as X, Y, and Z, you can use the formulas shown here, where X is I divided by width multiplied by layers, so that's the total number of layers. Y is equal to I minus X multiplied by height multiplied by layers divided by layers. And Z is equal to I minus X multiplied by width multiplied by layers minus Y multiplied by layers. And as you progress from X to Z, you can see how that each one becomes dependent on the one calculated before, so that Y includes the calculation for X and Z includes the calculations for X and Y. So what does this all mean for us? Well, we're using a flattened 3D array in our create cubes, and you'll see it inside of the for loop that is just here. So you want to create a single for loop which is counting around all of the elements in there, and then what we're doing is we're using the actual X, Y, and Z values of the cube to position them in 3D space. And that's why I need to convert from the index value of the cube in that array back to its actual position so that we can put it there. So you'll see inside of this loop where I've used those equations that I gave you just before. So first of all, we're going to set the X value for the cube to be I divided by width multiplied by layer. Now, I haven't calculated any others because they're actually sort of integrated into the next part of the code. So the cube's position at whatever cube we're talking about in that single array is going to be a new vector 3 at position X that we just calculated here. They're all going at Y. We're not worried about the particular height at the moment. And then the Z value is this calculation here, which I just showed you on the previous slide as the calculation for the Y. But remember, we've mixed these around because the X and the Y plane, the X and the Z plane is the one on the ground that we're working with. And so the Y now becomes the height instead. Now, once we've done that with this instantiated copy of the cube that you can see here, we're then putting that cube after we've positioned it into our array. After looping all the way through that, we then destroy our little copy prefab that we made because we don't need it anymore, and return the cubes, which will come back up to our start. And they've been instantiated, so they're going to appear in the hierarchy. With that done, save your code, switch back to Unity, get your code and attach it to your landscape object that you've created, and we will press play and have a look at what we get. It will create, in this case, I've got 100, 102 in my layers. You might have it bigger because it was set originally back in the script as larger than that. But whatever you get, multiply those three things together, and that's how many cubes you're going to get positioned according to their X and Z positions in that, internalized 3D array that we've flattened out. And if we just zoom in here, you'll be able to grab one of these cubes and move it around, and you'll see that it's in there. They're very small, aren't they? Here we go. So there's one of my cubes there. And if I get in even closer, remember that all of the cubes are in here at the Y position. So any that are in the same X and Z value are going to be on top of each other. And in this case, I've got 2 layers. So in each position, you'll see that I've got 2 cubes in there. When we come back in part 2 of this series, we'll start to add the Perlin noise over this landscape of cubes that we've created. And I know we haven't even looked at the job system yet, but trust me, you need to understand exactly what's going on and just how many cubes you're dealing with to really get the full appreciation of how we're going to optimize it. Thanks for watching. Please support the development of more superb online learning content by subscribing, and as always, visit holistic3d.com to learn more about awesome games development books and tutorials.